Okay, hi everybody. Hope you had a great week. I'm back again with a video about um, the halfway people. I hope that you're not getting too bored with it, but it's going to show how we figure out how old this Earth is by radioactively dating rocks. So here is what you need to download. You may notice that it says radioactive decay curve, and that now we've changed to half lives instead of half times. You'll see why in a little bit. So if you could please download this, go to the classroom and download this now onto your computer or iPad or phone, whatever you're watching this on. You're going to need this to do your problems. And then, so go ahead and pause the video and download this page from the Google Classroom onto your device right now. Okay, I hope you could do that. And now we're going to get right into it with Halfway Heather. Halfway Heather takes 8 days to do half of whatever she has left to do. So with the 16 problem homework, it takes her 8 days to do 8 problems. 8 problems because that is the half of the problems. And then the next 8 days to do half of those problems, which would be 4. 4 is half of 8. Then 2, because 2 is half of 4, etc. So she starts mowing the lawn. She started mowing the lawn 32 days ago. So what percent of the lawn still needs to be done today? That's your do now. So on your graph, go ahead and see if you can figure that out now. If you're having trouble answering this, you need to watch the Halfway Harry video that I posted earlier this week. That will really help you with this lesson. All right, turn it off. Do your do now. See you back in a little bit. Okay, I hope you're back, and let's see if we can figure this out. So 32 days ago, she started mowing the lawn. 32 days, well, let's see why that is. Well, let me shrink this down so you can see it better. And let's go and figure this one out. So 100%. 100% remaining must have been at 0 days, right? So each one of these numbers down here represents a half time, what we're calling a half time, but it will become a half life when we start talking about radioactivity. But what does each one of these mean? Well, it's 8 days, 8 days to do half. So each one of these half times is 8 days. So that's 8, 8, 8, and 8, all the way along. Now, she started mowing the lawn 32 days ago. What that means is that that was 8 days. It's 8 days to do half the lawn. So let's see where this is. Oh, yeah, it must be because 50% represents 1 half time, right? She mowed half the lawn, 50%. Now half of that, half of this 50% must be 25, which is right here. What does that correspond to? Well, that is 2 half times, which is 8 plus 8. That must be 16 days. So it's 8 days here, 16 days here. She's at 25% of the lawn right now. Well, another 8 days must be half of 25. Half of 25 is 12 and a half. That's about right here. Aha, check that out. That's 3 half times. That makes sense, right? So this must be at 8, 16, and now we're at 24 days. Now the problem says she mowed the lawn 32 days ago. So 32 days would be right here because 8 plus 24 is 32. And half of 12 and a half is 6 and a quarter. 6 1/4 is right here. Ooh, it works out. Look at that. So the question asks, what percent of the lawn needs to be done? Well, it looks like she's done everything except for the last 6 1/4%. So that must be our answer. She still needs to mow 6.25% of the lawn. Okay? All right. So now we're done with the halfway people. This is going to lead into what I hope will be helping you understand how we know the age of our Earth. All right, let's go ahead. So let's just talk about this graph first of all. This graph is kind of magical. It's pretty amazing. I want you to check this out. Wherever you are on the graph, let's just pick 64. Let's just say 64%. Well, let's look over here. 64% is right there. What is that? What is this number? Well, if you divide 1 into 5 equal pieces, right, that's a fifth. It's 1/5, 2/5, 3/5, 4/5, 5/5. 5/5 is 1. Now, if you use decimals, right, 1/5, that's the same as 2/10, right? You multiply the top by 2, you multiply the bottom by 2, you get 2/10. So 0.5 is the same as 0.2. So each one of these is a 0.2, right? So let's do an example here. So every line, so this would be what? 1.2 right there. And that would be 1.4. It's hard to write small with this pen. 1.6 right there. And 1.8 right there. And then 2 would be the next one, right? Well, let's just check this out. So what is this? So there's 0.1, 0.1, 0.2. Here's 0.4. So this must be 0.6, right? 64. And it corresponds to 0.6. Well, let's go over 1 half-life, or 1 half-time. So if we go over 1 half-time, that's how wide is that? Well, that is a width of this much, right? From there to there is 1 half-time. Well, if we go over 1 half-time, it's 5 of these 0.2s, or a 1, right? So that would be 1, 2, 3, 4, 5. We would stop there. Now, this is right here, 1 half-time, and that corresponds to this number right there. And what is that? Well, that's 1.2, 1.4, 1.6, right? 1.6 percent remaining. Well, look at that. This is 0.6, and this is 1.6, and that is exactly 32. Let me change colors here. 32. So no matter where you start on this curve, if you go over to the right 1 half-time or half-life, you will cut the percent remaining in half. Let's do it one more time, see if it works again. So here to here is another half-time, right? Let me change colors again. This is getting ridiculous. All right. from here to there, okay, is 1/2 time. Well, where is that on the curve? If we go here, I can't hit the margin with my hand anywhere. Okay, if I go here, right, what is that? Well, that is 16. What? 16 is half of 32. Let's do it again. Do I have another color? Let me try yellow. We go over 1/2. We go over 1/2 time to the right to 3.6. And now we're down here. And what is that? Oh, that's 8, half of 16. So basically what this curve does is it follows the line that corresponds to how far do you go down the percentages so that it's half every time you go to another half time. Okay? So this is called a decay curve. And it's a special kind of decay curve that is good for radioactivity. Why is that? Well, radioactive elements are in our Earth. In fact, that's what's keeping the inside of our Earth very warm and melted. That's why we have earthquakes, because it's like we're on a big waterbed, and when the Earth shakes, it's all liquid under there, all magma, melted rock. So radioactivity comes from elements that are unstable. They have an unstable nucleus, and they shoot out energy and particles. I want to show you a video that actually shows that. So check this out. This is a Geiger counter. It makes little noises every time a piece of energy or piece of particle hits it. And when this rock gets close to it, this is a piece of uranium right here, all of those little clicks are showing you when energy is being given off from that rock. Okay, we're back. So this is a piece of uranium ore, or a rock that contains a lot of uranium. Uranium is a great rock for dating how old parts of the Earth are. So when you hear those sounds and the particles being given off, they're being given off with a half-life, the same regular decay rate that you saw on the curve and that we've been working with the half-wave family. So it turns out that we can work backwards, just like we did with that halfway Harry problem. If we find a rock and it's giving off a certain amount of radiation, we can actually figure out how old that rock is or when it was actually formed. So we're going to redefine half time to be half-life at this point. So what is a half-life? A half-life is the amount of time it takes for half of a radioactive element to turn into a stable element. Or in other words, to stop giving off radiation. So we can tell how much radiation something has by measuring it. And what does that mean? Well, here is a picture of uranium-238. Uranium-238 is not stable. You see all those protons and neutrons in the nucleus? They are really tight in there. And you remember from science class before that a lot of positive charges stuck together, they all want to repel each other and explode out. Well, they explode out with these different pieces of things and energy, and that's called radiation. Now, when this radiation happens, it actually turns into a stable element, and this is lead-206. This is after the ancient Latin word plumbum, That's why the symbol is Pb, but it means lead, lead-206. Okay, so this uranium turns into lead-206 at a constant rate that follows, not a constant rate, but a diminishing or going down the curve rate that we saw on that graph. So in order to understand how this works, I have to introduce you to this mineral called zircon. Zircon, I know it sounds like a comic book bad guy character, but it's actually the name of a mineral. Zircon is in lots of rocks, so that's good because it means we can use it. And what happens is when it forms, it's all melted, and then when it solidifies, it brings in uranium atoms, but it does not bring in very much lead. That's important. I'll tell you why. So, if there is if there is only uranium in the rock when it first forms and there's no lead, that means we can measure the amount of uranium that's left and how much lead has formed. And that's going to give us an idea of how long ago this rock formed if we know the half-life of uranium. Well, the half-life of uranium is huge, 4.5 billion years. That's the half-life of uranium. In other words, it takes 4.5 billion years for uranium to decay 1/2 of itself. All right, so let's take a look at this. This looks complicated, but I'll explain it to you. I think you'll be able to get it. So if we look over here at this bunch of atoms, this would represent the rock when it first formed, and all the uranium is uranium. It hasn't decayed yet. This would be at time 0. Then, in one half-life, or in this case for uranium, it would be 4.5 billion years, you have all of your uranium that's in the rock, and half of it turns to lead in 4.5 billion years. You still have half the uranium left, and now it has half lead. So if I took this rock and I measured it here, I would know how old that rock is. Well, it must be, if it has half, you can see here that these little teal-colored atoms, oh, you can't touch the margin on this thing at all or it changes its page. You can see that these little teal-colored dots, those are all lead. Half of these maroon ones, have turned into teal-colored ones. And so that's called the daughter product. The daughter product means that it came from this. It's almost like this is the parent and that's the child, okay? So what happens here is we know at this point that our rock would be 4.5 billion years old. Now, this would be impossible here on Earth because our Earth is only 4.6 billion years old, but let's take it a step further. After another 4.5 billion years, half of the uranium that's left would turn into lead also. That would leave us with 3/4 lead and 1/4 uranium. That would tell us that 2 4.5 billion year chunks have gone by of time, and that's 9 billion years, right? 9 billion years. Well, let's take it one step further. In another 4.5 billion years, that piece, that little piece, that 1/4 piece of uranium, now half of that is gone, and now we have 7/8 lead and 1/8 uranium, because half of 1/4 is 1/8, right? And that's what's left. If you look on this graph over here, that's exactly what this shows. Here at time 0, we have 100% uranium. In one half-life, which is equal to 4.5 billion years, it's 50%, which would be here, right? Only 50% left. Now in another half-life, you've got 25% left. 25% would be a quarter. And in another 4.5 billion years, you have only 12.5%. Well, that should be 12.5. And what is that? Well, that's 1/8. 1/8 is left. Okay, so this curve right here shows how radiation is disappearing. But check this out. The lead is going up the same amount as this uranium is going down. So if we check out how much lead there is at any time versus how much uranium there is at any time, we can figure out how many half-lives have gone by. If we can figure out how many half-lives have gone by, we can figure out how old that rock is. All right, let's try a problem, okay? Let's try this one together and see if you can follow along. So a rock has been analyzed and it's found to contain 55% of its original uranium. Well, where is 55%? 55% is right here under 56, right? That would be 55. So we follow the curve over to here, right? 55% is a little bit past here, but we'll call it, on this line to make it easier to talk about. So here we go. What is this number right here? What is that number? That number is 0.2, 0.4, 0.6. That must be 0.8, right? So in other words, this rock has 55% left, which means this is 0.8 of a half-life. Well, what is 0.8 of a half-life? Well, that would be 4.6, right? 4.6 is one half-life of uranium, and we have to multiply that by 0.8, and that's how we're going to do this problem. So if we do that, we see that there is a 3.6 billion years, so that means the rock is 3.6 billion years old. Cool. So if you look, you could do this for any rock, for any age, depending on how much uranium it has. And how do we know what it started with? Well, we know because of the lead that's in the rock. If there's a certain amount of lead, then that means that only must have come from the uranium that the rock started with, right? So if it had 55% uranium, it must be 45% of the lead that it must have had, okay? So how much lead in there compared to how much uranium tells us the answer. Okay, I want you to try this one by yourself, see how you do. Turn off your video, try your hardest, use the curve. You can download a copy of that curve on your slide and try it. Okay, I hope you tried it by yourself. Let's figure out what this is. So In this case, we're using carbon-14. Carbon-14 comes from living things. So scientists actually use carbon-14 to date fossils, because fossils were once part of a living thing, right? Well, carbon-14 has a half-life of 6,000 years. So this is actually a good element to measure things that have lived fairly recently, not billions of years ago, but thousands of years ago. And in this particular problem, we have 16% left. So what do? Well, it looks like we need to go to our graph and figure out where 16% is. Well, 16% is right here. It's pretty easy because it's right on the graph. And if you follow it over, you'll see it hits the curve right here. That corresponds to 2.2, 2.4. That must be 2.6 half-lives, right? 2.6 half-lives. Well, 2.6 half-lives, if we have 2.6 of them, and each of them is 6,000, so this must be 6,000, this must be 6,000, and this is a piece of 6,000, right? This is 0.6 of 6,000. So if you multiply 6,000 by 2.6, you get 15,600. So this tree, when it was alive and taking in carbon-14, it must have been 15,600 years ago. Now, when that tree died, it doesn't live anymore, right? If you're an animal, you don't breathe. If you're a tree, you don't take in any more gas from the atmosphere. So that day, when that tree died, it stopped getting carbon-14. And from that day, the carbon-14 decayed and went to carbon-12, or actually, I think it's nitrogen. Yeah, it goes to nitrogen. And so we can figure out however much carbon-14 that tree has left in it, there's always a constant amount about in the atmosphere of carbon-14. And we know because it has 16% of that amount, now we can figure out how long ago that tree lived. Isn't that cool? I think that's awesome. Okay, so this is what we're going to do. I would like you to try your best to work these 7 problems. And I have given you what you need on the bottom here for 4 different radioactive elements. We've already used carbon-14 and uranium-238. This introduces you to potassium-40 and iodine-131. Each have a different half-life, so that you have to look at those to make sure you're using the right numbers. And you can always rewind this video and look at the problems that we've already done again. You're going to be using the same radioactive decay curve to figure out these problems. Okay? This, along with this video and the decay curve, will be in the classroom for you to do this week. Have a great weekend, and we'll see you next week for some more lessons. All right. Bye.